what the hell is computation?
It's very simple. Computation is the act of turning code and input chemicals into output chemicals and more code. So it's kind of like a cybernetic computation, but with stuff. So computation is the first kind of realistic route to program the assembly of matter by doing chemistry. And since most matter is chemical in origin, what I mean by that involves atoms and electrons. It's not, we're not working with neutrons or, I don't know, crazy particles we don't understand. It's, physical stuff. So computation, for me, computation was just the way to build an ontology that would make chemistry programmable. Because chemistry right now is kind of a bit analog, a bit ambiguous. And I thought, what is the most major transformation that's helped our digital world kind of work? And that was obviously the concept of the Turing machine and standardization. The microprocessors we have in our computers could take myriad of forms, right? The fact that we set on one form where we're going to use a binary switch, one high or low voltage, one or zero, and we just worked with that and miniaturized it and built abstraction on abstraction, abstraction on abstraction, gave us the technology we had today. I wondered if I could do the same thing in chemistry. The problem is that chemistry is a couple of hundred years old and, everyone does it their own different way. So I needed to come up with a principled way, a computation principle, a physical principle of programming matter and chemistry. And that's what computation is. So the short phrase is computation is to chemistry what computation is to mathematics. So computation is the act of programming chemistry, like computation is the act of programming mathematics.
Very cool. You have my money. That's a cool investor pitch. What advantages do you get digitizing the synthesis of chemical compounds for people that don't live in this world, which is most people? What advantages does that give you?
The key advantage is it allows you to remove ambiguity and therefore error. Because if you're making a molecule, and so let's say your molecule is 10 steps and you need those 10 steps to work, to get to the precise molecule you need to cure a disease or investigate some problem. If you're doing it by human labor, you're doing it very slowly and not reliably. So you don't know when you're going to get the molecule, right? So it's limited by human labor. And so the advantage is just really you can get it to be reliable, which means you can then start to scale it, which means you can make more complicated molecules, which means you can literally cure more diseases, which is like the ultimate goal. Right now, we have all these AIs that do kind of drug discovery, but they hallucinate and they
Yeah.
hallucinate molecules that cannot be made. What computation does, it grounds that and says we can remove those hallucinations, or indeed we take the hallucinations which turn out to be prophecy rather than just fantasy and do it quickly. And so there's the other limitations that people don't think this can be done. So they're just limited by manual labor, which limits how far you can go into chemical space. So with computation, you can go further and you can go there more reliably and you can go there more quickly. So I guess computation is to chemistry what the jet engine was to flight.
Really cool. Maybe explain that word chemical space. What exactly does that mean? I think maybe people might have some intuition of what that means, but your intuition is no doubt a lot more expansive.
Well, let's take outer space. What is outer space? Outer space is the universe around us in which there's a solar system, and then beyond the solar system, our galaxy, and then our galaxy is in a universe with lots of other galaxies, and we're all moving away. So there are physical things we can see with light. Chemical space is a bit different. There's chemical space we know, that is the molecules that we've made, and they have a particular signature, which is their molecular formula and their shape. So all molecule has a shape and a formula, which is just the atoms and its weight, right? You can characterize it by that composition. So chemical space, therefore, kind of known chemical space is all the molecules we know, like all the stars we know. We look up in the sky and we can see, Alpha Centauri and all these things, right? Great. So there's known chemical space where are all molecules we know. But there's something really interesting about chemistry is molecules can be added together, and under the right conditions, they can make a new molecule. So chemical space is a bit like mathematical space, prime number space, let's say, because we know all the prime numbers between, the bottom and all the way to a number that there's someone somewhere that has the largest verified prime, but they don't know where the next one is. Um, but obviously the next one will turn up when we find it. And so, and remember, prime numbers are just numbers that are divisible by themselves or one, right? So they're fundamental units. Whereas I'm saying molecules can be added together. So I think that chemical space is a little bit like mathematics, but it's physical. And as you can count through chemical space, add molecules together, you make new ones. So there's the known chemical space. There's the molecules we know exist. That we have we've characterized, we've written down on our map. And then there's the known unknowns, which is where we have reactions we know will work. And, you add A
Yes.
to B and you get AB. So we've got our known unknowns. And then, which is bigger. And then there's the unknown unknowns, where there are new
Yes.
reactions and new molecules. So chemical space starts from a physical reality and then goes into the holy cow, we don't know what's going on. So that's kind of what
Yes.
chemical space is. And it's bigger than outer space. So there are more molecules possible for drug-like molecules in the right kind of region than there are stars in the universe,
Very cool.
by a very large margin.
So this idea that the drugs that we use today are sort of state of the art best that we can do is just ridiculously wrong. It's entirely wrong. Every drug could probably be far better in terms of efficacy, in terms of reducing side effects. It could just be there's so many more ways that the drugs that we use can be improved.
That's a good point. I hadn't thought about it in that way. I mean, let's say what you're saying is like, let's take the top drug that's really good at doing its thing, and imagine if we had infinite money and time, that we could find another one that was better.
Yeah.
I think that's right. Because look, because chemical space is infinite, there should be other molecules that are better, that have less side effects according to your test, right? That you will have. So yeah, I mean, chemical space is so big, it's impossible to imagine. You could say, if I take like a mole of water, a mole is a kind of the units we use in chemistry. So in water, so a mole has 10 to the 23 molecules. So water is the density of water is 1 gram, so 18 grams per mole. So, and that's 18 milliliters. So 18 milliliters is like a shot glass kind of. Take a shot glass of water that has 10 to the 23 individual water molecules in it. There's only 10 to the 23 stars in the entire universe.
Yeah, it's
So
wild.
there's basically as many molecules of water as there are stars in the universe in 18 mil when you drink a shot.
Yeah.
So the numbers are big. And so the fascinating thing about chemistry is like, we have all these chemists who are thinking about chemical space, but they're not thinking about chemical space. They're thinking about a mathematical fictitious space they can't navigate. But yeah, it's huge. And I think there are plenty of drugs out there. The cure for cancer is in chemical space. We just got to go
Yes.
find it.
Yeah, like, wouldn't it even be the case you could take that further, that the probability that any drug we use today is the optimal drug for what we use it for is probably close to zero, just because, as you say, that the amount of chemical space that we've explored might be tiny, tiny fractions, like just Earth in our universe in terms of the entire space.
Yeah, that's right. But
Yeah.
what you could probably say is like, actually, some of the molecules have got, you go up the curve of basically good, 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 good. And then it's like, well, although there's an infinite number of molecules that might be up or down a bit, we're pretty much there and it's good,
Correct.
right? And there's certain examples. And there's also molecules produced by evolution, which are the best compromise for all life on Earth. Take insulin. That's a really interesting molecule,
Mm,
right? Which is co-evolved, right? Produced by biology. There's other ways of doing insulin's job, but it just so happens that insulin has been encoded, right? So I think kind of um, chemical space and the way that evolution works, they're kind of really connected together. One example as well, which is a bit weird, is you think about the opiates, the class of the natural opiates. And these are the molecules you find in, say, poppy seeds.
yes.
Well, it's really interesting that opiates hit the brain of mammals. Well, is it? The poppy seed, by accident, was making random metabolites just as a result of some errors. Then when that error happened in evolution, the animals that ate the poppy seed were like, "Well, this is good. I kind of like that. I can trip or whatever it is, right? Or I eat it to get rid of some pain, or I don't know how it would work, but something like that." So the
Yeah,
animals going back and eating those poppy plants and then spreading the seed far and wide was a synergistic process which amplified the production of that molecule in the natural environment. So it's kind of weird that
yeah,
that chemistry has co-evolved with biology. That's kind of cool. Think about it.
very
Chemistry
cool.
as a dead thing has co-evolved with biology, which is a living thing.
Yes. So is the computer a physical box with like a keyboard and the periodic table in it? Is that a thing?
One day it could be. Right
One
now,
day it
the
could.
computer today is a series of modules that understand the because I so when I came up with the concept of the computer, I was ridiculed um, and ridiculed. I don't know why it was ridiculed. I mean, it wasn't that bad an idea. And so people were like, "Well, we don't need this thing," and and not only did I is it a box, but it had to be an operating system, a programming language, and a firmware. So you know about computers. Computers kind of they have a set of instructions that are kind of hardwired to turn the computer on and display on. That's kind of the firmware. And then you have the operating system that lays on top of that, which you accesses the firmware. And then on top of the operating system, you have your software that allows your applications to run and then keeps going up in abstraction. So I had to build the whole damn thing. And so, and then the reason I knew it was going to work is because obviously it is based on the periodic table. And the periodic table is digitized because it's quantized, means that elements have well defined um, uh, properties. So it's a box. There are some ways of doing reactions in the box. There's a place to slot in the input reagents. There's a place to take the result out. But you have to do the process of chemistry, and the process of chemistry normally takes 6 years to train a human to do, and they all do it slightly differently, and they're all really cool. And so the computer is a compromise of 200 years of chemical genius.
I sort of assumed that some of this was already in the industrial chemical industry. You know, like how much paracetamol, Viagra, whatever chemical do we produce every day? I sort of assumed that there was chemical operating systems that were in place for that type of infrastructure.
Oh yeah, there are bespoke individual
Right.
programs for making things that you're making on the ton scale.
Right.
And so that doesn't, and so so the other, so it was kind of interesting. So all the chemists said, what you're doing is ridiculous and not needed. And all the chemical engineers said, oh, what you're doing is obvious and we already have done it.
Right.
But so I was kind of like, shit. Um, and so what the truth in the situation was is that the unit operations are using chemical engineering to make big plant, and the concepts are applied on a place on a factory by factory basis. And yes, there are technologies of factories, but they're pretty kind of there's not that many factories on planet Earth. Whereas a chemist has to be able to do everything. And what I wanted to do is find a compromise and join them together. It's a bit like there's certain um, devices you would make. Like you could make good old days, if we remember, say, the portable cassette player that would play music, or we might have a flashlight that we have. Well, if I've got my iPhone and I might buy a walkie talkie, right? There are three specific things where I've got communication, I've got light, and I've got music. Well, in my iPhone and a lot of other phones, I have a flashlight, I can listen to music, and I can phone people. So it's kind of about convergence into a modular
Right.
system to have more what we call interoperability. So what I've done on the same, it's like that's why it's kind of funny because everyone's like, it's completely stupid and it's completely obvious, and so you kind of it's very frustrating. Not yeah, it was frustrating, but it was kind
That's
of
got to be
more
a
funny.
positive signal, though, almost, because like, the people that are saying it's stupid are probably maybe a little bit jealous they didn't come up with it themselves, and they're just kind of maybe a little bit trying to be haters. And then the people that say it's obvious are like, well, yeah, we've been getting actual real utility out of this for years. I can't believe that the non-industrial chemists haven't thought of this. That's got to be positive signal for you, kind of working in the middle and trying to expand a category.
Mm, I mean, if someone says you're stupid and someone says it's obvious, I mean, there are a large number of sets where both of those things are correct at the same time, right?
Yeah.
It's like, it's obvious if you walk in the middle of a busy road and you don't look both ways, at some point you're going to get knocked over. And that is a stupid thing to do. Um, but I get your point. And I mean, and obviously my job as a scientist, I mean, I am first and foremost a scientist who is very curious. I am a scientist who happens to be a chemist. And there's a lot of scientists do chemistry, but not all chemists are scientists, right?
Yeah.
Lots of chemists do other things. They want to, they're trying to develop a process or they're trying to purify something. And I'm not saying that that's bad. I'm not putting any quality on it. I'm just saying I am a very curious individual who just basically messes around with science, and my science is chemistry. So I actually have to be slightly an anarchist and do random stuff,
Yes.
and that other people think is ridiculous. So when people say something is ridiculous, that is actually okay,
Yeah.
right? Because that means you're doing something new. But it could be just ridiculous, and so you can stop doing that as soon as possible. So it's okay, right? You know, I'm very happy to be told it's completely pointless. As long as I am trying to solve a problem and
Yeah.
do something new, and my problem was, I mean, I only built the computer to solve the origin of life, right? Chemify is the result of that quest. The fact we're attempting to build the biggest chemistry company to make molecules on demand and discover molecules that could be drugs and new materials is a side effect of me wanting to map chemical space to find out how evolution got going.
I get the sense you like really small, easy problems, very solvable, simple type tasks.
It is a simple problem. I mean, the thing is, right? It's a really, I always work, I'm being a scientist who has to work across lots of disciplines. I have to um, work on simple problems that everyone thinks is obvious. I think actually where you get some people who are a bit jealous, but I mean, jealousy is a funny human thing anyway, right? I don't think people are
Yeah.
really that jealous because I like, people jealous of Chemify. I'm like, really? You understand how hard this is, right?
Yeah.
It's not like I'm taking the 50 million and like, hanging out in
Off to
Monte
Barbados.
Carlo or so, yeah, yeah. I'm just like, well, the money. What we've got to try and do is turn that resource into a sustainable company
Yeah.
using a brand new technology that probably is not fit for purpose yet, and we have to do R&D at the same time. So it's like continually finding the minimum viable route to get to the market to give people what they want now, get them
Yes.
excited about what we can do tomorrow, and to bear with us while our steaming dumpster fire of a company becomes into, I don't know, the Pegasus of tomorrow. And I mean, it's good. There's half Pegasus, half dumpster fire, depending how you look at it. And so first principles thinking requires you to be simple. And I would always argue, like, it's not complicated. If I say something to someone and I don't know what I'm talking about, it's always my fault, not their fault, right? Because, I'm not saying that I'm responsible if someone is absolutely illiterate in every respect, but there should be a way for me to translate without patronizing or dumbing down the basic concept of what we're
Yes.
doing to anybody. You have
Yes.
to. And to say that you can't do that. So no, you have to make it simple and it has to be from first principles. And yeah, it's pretty audacious. The layers, there's so many layers and the layers are hard. Sure. Yeah. I agree. It's audacious, but better than not, it's better to try and fail than to not try.
I couldn't agree more. What is the ultimate moonshot, everything goes absolutely perfect vision in 10 years? Like, what does the world look like? You've been collecting Nobel Prizes like they're Pokemon. Everything is just going so well for you. Like, what does that world look like in 10 years?
Um, I mean, it's very hard for somebody in my position or anybody actually to imagine the future, even if it all goes well. Because even if what I think goes well, it's going to be so much more.
Yes.
But I think that it would be fair to say that every new molecule made on planet Earth will go through the programming language. That will have a Git for chemistry.
Right.
That will also, and it will turn into programmable matter. That drug discovery will take, I don't know, this will probably take more than 10 years, or probably maybe take 50 or something, 60 years. but you'll be able to make a personalized drug, small molecules for individuals that they need. In fact, what we'll do is no one will get ill in the future. We'll actually have real-time gene sequencing. We'll work out when a mutation is manifest, and we'll then synthesize the molecule to bind to the RNA that is producing that defect and even stop that protein from being made.
Crazy.
So, I think so that would be my wildest dream, I suppose. But I think what I have to be happy to do is to build an underpinning technology that others will use in ways I cannot imagine. I have this. I've written a couple of kind of stories I give investors. And one is like the story of the ENIAC being built, the first programmable computer in the Princeton area in the late 40s, I think. It had like 5 million soldered joints and a few 100,000 transistors. And when you turned it on, the local power from the town used to flip out and stuff. And if you say, well, you got this proof of it working, then if you take, say, the engineer who built the ENIAC and said, I'm going to take you a time machine to see your great, great, great grandkids. And then you say, oh, hi, grandpa. I'm going to call an Uber, right? And you're like, how do you call Uber? So, well, I've got this thing called a phone. It allows me to communicate via a local network to call a car. And it knows my global positioning using a satellite in space. And I basically determine real-time availability of Uber on my phone that connects to a computer. So the poor guy is like imagining that ENIAC, he must be like, gosh, this computer must be the size of a skyscraper. How does it work? Can I see it? And then you pull your phone out of your pocket.
Yeah. Yeah.
So I have no idea what's going to happen in 10 years, let alone 50 years. But I do think if we build a universal programming language and make sure it's extensible and Turing complete and all that jazz, it's all the things, so many interesting things will happen. It will be unbounded.
Yeah. You brought up a really interesting point there, which is personalized medicine. So not just creating new compounds in chemical space, but optimizing it very specifically for the exact internal biological system of someone who is sick or wanting to get high at a rave, or any of the other 100 reasons that people like that. How do you even start to think about that sort of problem of personalizing the new drug to the entire biological system? Like that's you got to say that's complex.
That's way above my pay grade. No, it's not
Right.
that complex, but it requires the following technologies to converge, right?
Yeah.
First one is, if I was going to imagine it and write a science fiction book on it, I'd say, right, in the future, people don't have big chemistry sets. They'll have a little chip
Okay.
somewhere, maybe I don't know, in their nose, in their stomach, somewhere. And that chip would use available resources from their food and break it down for chemistry. And then
Okay.
it would turn that into molecules you need on the the scale that is absolutely minimum needed, and just produce new drugs all the time. And then you'll have another chip that's sequencing your entire genome all the time, so you know how the mutations are going. And because you've got real time telemetry on evolution and your requirements, you make the molecules in such small amounts. You don't need that much. Hell, you could have it organ specific. Put a
Yeah.
chip on every organ. I'm just making this up, right? As you can go. But so, and that's how you do personalized medicine. But right now, we're so far away from that. We're kind of in the era of you have to listen to the radio, and the music that will be turned on is what you're going to listen to. Versus, I have every CD that's ever been done, put on a database somewhere, and I can call that up now.
Yeah.
And again, no one would ever have conceived of that 100 years ago. Could just about have conceived of the gramophone. So, and it's not complicated, it's intricate, right?
What's the
It,
difference?
very simple things made and put together in a network of stuff gives you functionality that looks overwhelmingly complicated
Right.
because there's so many parts to understand, and no one individual on the planet will be able to understand them. But individual bits you can do. And it's very important, in the way I communicate science, is that we need to make sure that people understand science and technology is in everyone's grasp, right? And yes, it's hard, and there's just a lot. But if you specialize in one thing, you can basically grasp that. Well, we've got to be more flexible. It's like being able to rapidly specialize in a lot of different things. But that's probably another conversation. But yeah, I don't know where personal meds are going to go. I think it will be very interesting to see how humans develop that
Yeah.
technology, because there needs to be some step changes in technology, right? So I need to basically build the technology that allows you to make molecules on demand. There needs to be a new technology in molecular delivery. There needs to be a new technology in personalized gene sequencing.
Yeah.
I mean, there will be, right? Why not?
Yeah.
It's not conceptually that hard. There might be things of kind of practical reality, like, you know, I think there are people saying, oh, you don't need a computer. You just need to, in your house, you just need to go to a big mainframe, right? And now the fact that everything is a computer, like it's wild.
It's such a cool vision, and I love the way you speak about it. It's so fun. Do you see a consumer computer? Like, do you think in 2035 I will wake up in the morning and I'll turn on my espresso machine, get my double espresso, and then I'll turn on my computer and get 300 micrograms of LSD or some modified LSD that's perfect for my body based on my distribution of serotonin receptors and all the rest? And like, is that plausible in your view?
I mean, if the people want that and it's legal, I mean,
Yeah.
sure. I mean,
Legality is the issue, yeah.
no, I mean, no, it's not an issue, right? I think so I think that my job as a scientist is to ask, why does the universe work? And then my job as a technologist is to say, how can I make the universe work? And as an entrepreneur is to basically give people new possibilities and the market will pay. And then the job of the politician is to change the infrastructure, the legal infrastructure, to say, well, some things are allowed and some things are disallowed. This is one of the reasons why I do not buy on any level the fact that I have a responsibility for chemical weapons or drugs or whatever. No, no. That's not what humanity pays me to do, right? Society pays me to ask questions, right? And we also pay politicians to make the law. And then we
Yeah.
have, and I think what happened right now in this kind of age of, oh, let's all be politically correct and let's all have existential doubt about the future. I have to basically censor myself. I'm an anarchist. It's like, I will do stuff for shits and giggles, you know?
Giant news. We created a completely free ebook titled 26 Neuroscience Books for 2026. I've read over 100 neuroscience books in my life, and with Christmas just around the corner, I thought I would help people find the perfect book for them or to buy for someone in their life. It includes really nice science-based illustrations, an accessibility guide, and personally written segments for each book and the impression they left on me. I also asked 100 top scientists like Dr. Mike Levin, Anil Seth, Nick Lane, and many more what their favorite science book is, and you can find all of those included at the end. If you want to support the channel, you can also purchase a beautiful physical paperback copy, also a perfect stocking filler. We put a lot of effort into our first giant shoulder product, and we cannot wait to hear your thoughts. Check it out in the link below. Again, it's completely free.